slide. Yeah. So here, main concept, we want to look at critical points. Yeah. So critical points, when we look at trajectories, there is some special points. Yeah. Because it could be more than one, yeah, several. Later you will see we have, we have more than one critical points. Yeah. So the definition of the critical points, when we look at the slope expression, dy2 over dy1 slope. Yeah. So in the y1, y2 plane, yeah, so each trajectory, there is an equation involving y1, y2. Yeah. So if we calculate dy2 over dy1, this fraction is not defined. Okay? Yeah. So there is no valid value for it. Yeah. Here it says undetermined. Yeah. So I feel this word may not be as good as the not defined. It is not defined. Yeah. So undetermined, so it may give you impression we can determine it later. Yeah. After we pay some effort, we can determine it. Yeah. Actually, no matter how much effort you pay, you cannot determine it. Yeah. 0, 0, how can you assign a valid value to it? You cannot. Nobody can assign a valid value to the slope. Yeah. All right. Next, we want to study 5 types of the critical points. 5 different types. Yeah. All right. First, improper node. Improper node. Yeah. We need to define the first type. Yeah. So what's the meaning? Yeah. So the one, yeah, we saw before. Yeah. Improper. So a critical point at which all trajectories except for 2 of the straight line, except these 2 trajectories, yeah, except of them, have the same limiting directions of tangent. Okay? Say, okay, if we don't look at these 2 straight lines, yeah, these 2 straight lines, there all other trajectories, you can see there is a common tangent. Common tangent. Okay? Yeah. Yeah. But those 2 lines, yeah, so now yeah. All right, limiting direction of the tangent. Yeah. That's improper. Yeah. Cool. Then proper node, different type. Second type, proper node. Yeah. Like this, yeah, proper node. Okay? Yeah. Yeah. So what's that? A critical point at which every trajectory has a definite limiting direction. Okay? Definite limiting direction. Yeah. Yeah. All right. Yeah. Yeah. And for any given direction, there is a trajectory having it as its limit direction. Yeah. The second type. Yeah. All right. Yeah. Example, yeah, simple example like this. Its characteristic equation, yeah, see double root, double real root, yeah. General solution, if you write general solution, C1, C2, yeah, C1, C2, like that, yeah. So now you can see, yeah, Y2 over Y1 constant, C2 over C1. So Y2 over Y1, the slope equals C2 over C1. Okay, yeah? So you can see just like that. Yeah. Right. So in this simple example, yeah, there is a problem. Yeah, if you look at this double root, why you write the general solution in this way? Yeah. Yeah. So that question, yeah, that question is a little deep. Yeah. because you need to study the eigenvector space, the space formed by eigenvectors. Yeah. So that's the theory. Yeah. Too complicated for us, yeah, because that whole theory. So we try to avoid that. Okay. Yeah, yeah, because here, how to explain that? Yeah, how to explain that? Yeah, why is that? Yeah, but there is some way to find it out. But that theory is too deep. Yeah, yeah, too deep. Yeah. So we do not go that far. Yeah, yeah. All right. Yeah. Otherwise, some of you may ask me, why you write this way, right? Because based on our impression before, you should have a t here, right? Yeah, be double root, you should have a t here, yeah. But with t or not, then you need to explore another structure. Yeah. If you only look at the characteristic equation, that's not enough to tell you the whole picture of the structure. Still, some hidden, deeper level hidden structure we need to calculate, okay? So we need to calculate, actually we need to work on that A minus lambda I2. We need to look at the whole matrix. Yeah, yeah, here. Yeah. So here I just give you some, simple explanation here. Yeah. Remember, we calculate characteristic equation. We use determinant of A minus lambda 2, I2. This, we solve this equation. Yeah. But this equation does not give us a whole picture. This equation does not give us whole picture of the structure. Okay? Some deeper level structure is not visible from this characteristic equation. Yeah. But how to see the whole picture of the structure? We do not calculate the determinant. Yeah. Determinant, because if you calculate determinant, you only take part of the information, not the whole information. Yeah. So you need to work on the matrix of this whole matrix directly. Okay? This matrix, you need to do factorization and factorize it in a special matrix structure. Yeah. Factorize, so left-hand side, one matrix, then the middle, another matrix. Yeah. Then you look at the structure in this matrix to tell you the whole picture of the structure. Yeah, yeah. So we won't go that far. Okay, we won't go that far. Yeah. Here I just let you know, because the determinant, you can imagine, you may have different A matrix. A matrix is different, A1, A2, but if you calculate determinant, they happen to be the same. That's possible, right? Yeah, yeah. Because we determinants, multiply the formula. You can have different way. You multiply things together, you get the same thing. Yeah, that could be the same thing. But actually, A1, A2, two different matrices, they should have different structure. Okay, but your characteristic equation the same, so it cannot tell you. So the same characteristic equation cannot tell you the difference of structure between A1, A2 if they have the same characteristic equation. Yeah. But this factorization, A1, A2, you will have different middle matrix. Yeah. The matrix in the middle. Yeah. It will tell you, more information. Yeah. So just give you some, description. Yeah. All right. Then, type 3, saddle point. Yeah. Well, saddle point is like this shape. Yeah. Yeah. description, a critical point at which there are two incoming trajectories, and two outgoing trajectories, yeah, and all the other trajectories in a neighborhood bypass this point. Yeah. Yeah. So do not pass through this point. Yeah. So you can see quite different from our first type. First type, yeah, all trajectory touch that critical point. Yeah. Yeah. So that's the saddle point. Yeah. All right. Example here. Yeah. So characteristic equation. Yeah. Two different roots. Yeah. Here. Yeah. You can see another information. If the characteristic equation has distinct roots, then the characteristic equation can give you, the structure we need. Yeah. All the structure we need. Okay? Yeah. That means we'll write the general solution without any different ways. Yeah. Only one way to write. Okay? Yeah, but if you have multiple roots, there you may have different ways to write the solution. Yeah. All right. So the general solution here, this way. Okay? Yeah. So only way to write, yeah, like that. Yeah. So then this time y1 times y2 is a constant. C1 times C2. Okay. Do you have idea? So what's the curve shape corresponds to, product of y1, y2 equals a constant? What's the name of the curve? Special name. Yeah. Yes, perfect. Hyperbola. Hyperbola. Yeah. Last time parabola, right? Last time we learned a parabola. So this time hyperbola. Yeah. You pronounce, better. Yeah. Hyperbola. Yeah. All right. Oh, yeah. So we finished that. Yeah. Number 3. Number 4. Center. Yeah. Center case, like that. Center case, there is a center. So then all trajectories around the center. Yeah. See? Yeah. No incoming, outgoing trajectories. Yeah. A critical point that is enclosed by infinite many closed trajectories. Yeah. Type 4. Okay. All right. So example like this equation, characteristic equation. Here you can see, yeah, two complex roots. Yeah. Lambda square equals 4. Yeah. Yeah. 2i. Yeah. So this time we may need to write, yeah, in the complex, the general solution complex form. Yeah. Because here it's not easy to write, real form. We like to write real form, but, with the complexity here, not easy to write a real form. Yeah. All right. But y1, y2, let's write y1, y2. Yeah. Yeah. Now we want to write the equation for trajectories. We want to, write an equation with y1, y2 and eliminating t. Yeah, eliminating. So we don't want to see t. Okay. Yeah. 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 So here, to do that, the second equation, I want to divide it by 2i. Yeah, 2i. Okay. So the right hand side, the structure similar to the right-hand side of y1 because we can do some cancellation. Okay, plus minus, we can do some cancellation. y1 plus y2 over 2i, yeah. So the second term cancel out. Okay, we double the first term. Yeah. All right. Then another one, y1 minus y2 over 2i, the first term cancel out. We double the second term. Okay, yeah. Then let's multiply these two equations, both sides. Multiply left-hand side, right-hand side, multiplication, and see what do we get. Okay, all right. y1 squared plus 1/4 times y2 squared equals a constant, 4 times C1, C2, constant. Okay, yeah. That equation. So when you see this equation, what's the curve? What type of curve it is? It's easier. This one, easier than last one. Look at the shape, you know. Yeah, oval, yeah. Ellipse, yeah, 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 so, yeah. The formulae they call ellipse, yeah. Although the oval shape, yeah.
Are all these like characteristic equations and stuff? These are specifically to these example pictures, right?
Yes,
Okay.
yeah, yeah.
I'll just clarify.
Right, good, yeah, yeah. So yeah, you can see, yeah, yeah. So you can see these types quite different. Yeah, the last type. Another type, last one. Yeah. Type number 5, spiral point. Yeah. This one, much harder than the first 4 types. I mean, when we look at a trajectory equation, much harder. Yeah. 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 All right. So let's look at the shape. From the name, you can see the shape, the spiral shape. All right. Yeah, like that. Yeah. Let's look at the description. A critical point about which the trajectory spiral approaching this point as t goes to infinity. Yeah. So goes to infinity. Yeah. 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 So here, let's derive the equation of each trajectory. Yeah. Yeah. Look at that example. Yeah. Simple example. Here you can see where A matrix is different. Okay. Critical points quite different. Yeah. From the matrix, it's hard to see it. Yeah. All right. So we need to look at the characteristic equation. Yeah. 2 complex roots. Complex roots this time. Yeah. Then the general solution, we need to use complex expressions. Yeah. All right. Eigenvectors, here we, complex value, yeah. Eigenvectors. All right. Then y1, y2, yeah, pretty complicated. y1, y2. Okay. So E function, see, real part, imaginary part. Okay, E function. Yeah. All right, y1, and y2 here. Yeah. So then I divide by both sides by I. Yeah. So we try to do some cancellation here. Okay, yeah. Similar to what we did in the previous one. Yeah. y1 plus y2 over I equals double first term. y1 minus y2 over I, double the second term. Yeah. All right. Now let's multiply these two equations and see what we get. y1 squared plus y2 squared equals 2 C1 C2, but with an e to the negative 2t. Here, this t is hard to eliminate it. It's hard to eliminate it. So let's keep it. Yeah, because from this equation we can see the spiral shape. Yeah. All right. Because if you don't look at the right-hand side, if you just look at the left-hand side, it's a circle, right? Yeah. Circle part. If the right-hand side is a constant, if we don't have E function, right-hand side is a constant, then it's an exact circle. Exact circle, all right? But add this E part, the radius, you need to keep changing the radius. Keep changing, okay? All right, so when T is a negative infinity number, the radius is positive infinity, okay? Positive infinity. So you start from very far from the origin, okay? Yeah, positive infinity, yeah. Because the radius is positive infinity, okay? Then, when you change T from negative infinity to positive infinity, where it's positive, this is 0, right? This is 0, yeah. So here you can see the radius. This side you see the radius part. Radius keeps shrinking, okay? Keeps shrinking, yeah. And at the end, the radius becomes 0, so you get to the origin, the critical point. Yeah. So it tells you, that spiral. Yeah. Yeah. So although we cannot eliminate this, but we can see the shape from this equation. Okay? Yeah. So that's the type 5. Yeah. Okay. Yeah. All right. Yeah. So, yeah, because sometimes when we study the trajectories, so we want to study critical points, and, trajectories. Yeah. Trajectories, after we get equations, we want to draw the graphs. Yeah. Draw the graphs with different constant, then we draw, many curves. Yeah. All right. All right. Next, qualitative methods for nonlinear systems. Qualitative, yeah. So when you see qualitative here, we do not try to solve nonlinear system, yeah. Because usually nonlinear system very hard to solve. In general, nonlinear system too hard to solve. Right. So when it is hard to solve, then we want to do some qualitative discussion. Yeah. So try to see some properties. Yeah. All right. So this part, we want to look at qualitative properties. Yeah. Study autonomous nonlinear system. Yeah. Autonomous. Yeah. Yeah. Because our trajectory, so if you look at the trajectory, yeah, that's the trajectory, yeah, so trajectory, so that's different. So autonomous, when we write the differential equation, f of y, you can see this f function, there is no x in it, only y. So that's the autonomous function, ODE. All right. So y1 prime, y2 prime, and you do not see the x or t, variable part. So that's the typical autonomous type. And for autonomous ODE, nonlinear, because F1, F2 could be very complicated, not necessarily linear. All right, so the critical point, how do you find the critical point? F1 equals 0 and F2, so when you find the F1 value, F2 value, both equal 0. Both equal 0. Both equal 0 because y1 derivative over y2 derivative 0 over 0. not defined. Yeah. That's the definition of critical points, not defined. Yeah. So you can see, if you can solve these two equations for certain special values y1, y2, then you can get all the critical points. Yeah. All right. Consider the case that there are several critical points. Yeah. So here there is a special way we study the critical point. Yeah, because we can have multiple critical points. Yeah, here. Yeah. More than one. Multiple critical points. Yeah. Multiple critical points, you can only have one critical point at the origin, other than at the most one. Other than one, all the other critical points cannot be at the origin. Yeah. But we feel if we can move the critical point to 0, then it's very convenient to study. Yeah. Yeah. Put the critical point to 0. Yeah. Yeah. As a center, yeah. Because origin, yeah. Center, yeah. That special point, put it at the center, then the formulation would be simpler. Okay? If it's not at the center, yeah. So then formulation could be more complicated. Yeah. So we want the simplest formulas. Yeah. So for that purpose, we like to shift. Yeah. We like to so when we study one particular critical point, yeah. So we will study one by one. Okay? 1, 2, 3. Yeah. One after another. Every time when we study a new critical point, we want to shift our axis, okay? Coordinate system. We want to move, do translation, translate our coordinate system and move the origin to that critical point. Yeah. So that's the typical way we study critical point. All right. So assume that A, B point coordinates is a critical point. Then we need to do translation operation. Okay? So we need to apply translation operation y1 tilde, yeah? So, because here we need to move to a different coordinate system. Yeah. y1, y2 is our current coordinate system. Yeah. Now we want to create a new coordinate system. In our new coordinate system, this critical point corresponds to the origin. Okay? Yeah. In the new coordinate system, y1 tilde, y2 tilde, you plug in y1 equals A, y2 equals B, 0, 0. Okay? So in the new coordinate system, y1 tilde, y2 tilde, the current critical point is at origin. Yeah. So in this new coordinate system, we want to get the simplest formulation. Yeah. Yeah. All right. So then, it's easier to see the behavior around the critical point. Right, yeah. Then, let's do the substitution. Yeah. So we introduce two variables, then we do substitution. All right. What kind of substitution? Yeah. All right. y1 prime, yeah. Go back to f1 function, y1 prime plus a, yeah, because that's y1, y2 tilde plus b. Yeah. Okay. Second one, y2 tilde prime, yeah, so then plug in. Yeah. Yeah. It looks a little complicated, although, yeah, it looks a little complicated, yeah. Yeah, but not too bad, yeah, not too bad. You just, each coordinate, you just plus one constant. Yeah. Plus one constant. Yeah. But you may see this tilde sign, right? On its head, a tilde sign. So you may feel a little annoying, right? The tilde sign. Yeah. Yeah. There, we do one thing I mentioned before. Yeah, something people frequently do in their math formulation. Yeah, we call abuse the notation. Abuse the notation. Okay? Here, yeah, the author, textbook, for simplicity, we drop that tilde. We drop that tilde. Okay? Yeah. For simplicity, you can see the tilde gone. Okay? Yeah. The tilde is gone. Yeah. Yeah. Because those two, they're just two symbols, right? Y1, Y2. After you add tilde, just the different symbols. Yeah. Yeah. But the reason we drop the tilde, because quite annoying, visually, right? Visually, not neat. Yeah. Something not quite neat. Okay. Yeah, impact psychology. Yeah, impact psychology, a little bit, because people like neat things. Yeah. It's not like a lot of things attached to it. Yeah. Yeah. So there, simplification. Okay. So you remove that, but it's a different coordinate system. It's a different coordinate system. Okay? Yeah. So you won't get confused with the original coordinate system. Yeah. Because you only look at this current critical point. Yeah. You want to look at behavior around the current critical point, dropping the tilde, it does not change anything. Studying the behavior around critical point. Yeah. So that's the reason we can draw. Okay? Yeah, we can draw. Yeah. 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 But all right, so here. Yeah. Do this for each critical point. Because now we have new equations. Then we study the critical point as we studied at the origin before. Okay? The A matrix, eigenvalue, eigenvector. But A matrix, there is a problem. A matrix, it's the linear part. Yeah, A times Y, it's a linear equation, right? But this F, F1, F2, they are not linear equations. How can you get an A? You cannot get an A. So it's not linear equations. Okay. So you cannot get an A. Yeah. So the next step, we do one approximation. So we call it linearization. We do linearization of F1, F2. Yeah. So the linearization, we want to use linear function to approximate F1, F2. Yeah. Can we use the linear function to approximate some arbitrary function? Use linear function to approximate. It looks too radical, right? Too aggressive? Too aggressive? Because f function could be very complicated. But linear function is so simple. How can you use a linear function so simple, straight line, plane, to approximate, very complicated function? The answer is, when you are very close to the critical point, that's a good approximation. If you live far away from critical point, bad approximation. Okay? Very close, critical point. The closer, the better approximation. Yeah. Okay? Yeah. So that's why we can do that. At least we can study the behavior in a small neighborhood of critical point. Okay? Yeah, all right. Yeah. Linearization of non-linear system. Yeah. Yeah. So, yeah, we will learn a theory. Yeah. Yeah. We still have 10 minutes. Yeah. So we, try to, convey the idea. Yeah. So we may not. So this part, I may not ask you to do a lot of work, yeah, but just to get some general background knowledge, okay, to enrich your background. Yeah. All right. Move a critical point from A, B point to the origin. Yeah. So the idea, the first step, we do translation like this. Yeah. So we can get a new form of equation. Yeah. So this time we just study critical point at origin case. Yeah. Now the key step, apply the linear approximation. Yeah. Linear approximation. Let's recall in calculus. Did you do linear approximation in calculus? Linear approximation in calculus. Yeah. Approximate. So you have a function that's not linear, sine, cosine, tangent, pretty complicated. Yeah. There is some special way you can write expression to approximate this function, yeah, preserving the linear term. Okay. Other terms throw away. You only take the linear term. That's the linear approximation. Yeah. So let's look at that. Okay. All right. So the f function could be very complicated, but we want to take the linear part. Okay. Yeah. Non-linear part. Yeah. Linear part. We extract all the linear terms out. Yeah. How to extract? Yeah. Later you will see. Later, we have some special way to extract the linear terms. So we put all the linear terms together, so we get an A matrix. Non-linear terms we throw into that H function. Okay? H function containing all the non-linear terms. So this is called a linearization. Okay? Yeah. All right. Then, linear approximation. Linearization, we throw away H function. That's the linearization. Okay? Yeah. So first linear approximation. Yeah. Yeah. In approximation, but we take out linear term. Yeah. So linearization, we only keep the linear term. Yeah. Throw away non-linear terms. That's linearization. Okay? Yeah. But this linearization, we want, because if you throw away some term, you want to make this term relatively small. Yeah. When it is small, the approximation is good. If the term is large, the approximation is not good. Okay? Small, so when the y vector close to 0, okay? The y vector very close to 0, then it is small. Okay? It is far away from 0, then it will be large. All right. Here, this linearization theorem. Yeah, this theorem tells us if we do linearization like this, yeah, here I only point out the critical sentence. Yeah, critical sentence. Condition could be complicated, and just description. Okay. All right. The critical sentence here is if we do linearization like this. Yeah. All right. Yeah. Yeah. There, 1, that's the original equation, that's the 1. Okay, equation 1, okay? May have the same kind of critical point as 3, yeah? Because that equation, the critical point type 3 of 5 different types, okay? But after we do linearization, we do not change the types, yeah, or a spiral point, yeah. So, yeah. If it's not a spiral point, then the same type. Yeah. If it is spiral point, then may not be the same. Yeah. May not be the same. So this theorem tells us if we do linearization, we can study at least a part of the behavior around the critical point. Part of the behavior, yeah. May not be 100%. So some special case, yeah. So that may cause some distortion, okay? A little distortion here. Yeah. Yeah. Other than this special case, then the remaining 4 types of critical point are preserved. Linearization, this process does not change critical behavior. All right, hope. All right, so that's the the idea. So here, just give you some idea. Some idea, so you learn, you can see how people study math, or how people study some, object. So here, mathematical object. That is complicated. So here we try to find some simplification ways to study some complicated math object. All right, free undamped pendulum. So here, so because we have for homework assignment number 2, we have a question of this pendulum. So let me, I only have 3 or 4 minutes. Let's say 3 minutes. So let's just look at the, differential equation of this pendulum. In physics, you learn, right? I remember I learned, this kind of figure in physics in junior high. All right. The angle usually small. Not large. If it's large, so then the motion is more complicated. If it is small, then we have good approximation. All right. So here, the weight mg, that direction. But it's an arc. This ball moves along this arc, So there is a tangent line, a tangent line. So the ball always moves along the tangent line of the arc, And there is this normal line, normal, perpendicular to the tangent line, So the force, this weight, it's a force. The force can be decomposed into 2 forces. One along the tangent line, another along the normal line. Decomposition. The decomposition, you use the, trig functions, sine, cosine, to give you the amount of force. All right, these 2 forces. All right. So the question. So mass m, length L, determine location. So the location function as a function of t. So we want to find that function. But location, so this is an arc. We know the arc. All right. So the length, radius L fixed. Radius L fixed. All right. So then the arc, all right, the length of the arc equals radius times the theta. Radius times the theta. All right, so here, let me just give you the equation. Restoring force, this force component along the tangent line, restoring force, mg sine theta. Okay, mg sine theta. Force of acceleration displacement double prime. That's m mass times L times theta. L times theta, that's this arc, length of the arc. Arc we treat as displacement, double prime, that's L theta double prime. Newton's second law. This is Newton's second law. Newton's second law equals this force, but direction, theta direction. Theta positive direction is that. So here, look at the positive direction, okay? But this force is negative, negative to the positive direction of theta. So this side negative, you move to the left-hand side, it's positive, plus. So that's the differential equation. Okay? So from this model, you only need to know, after this discussion, this is the differential equation. K is this one. Okay? So after the model, we need to solve this differential equation. Okay? All right. Let me stop here. Yeah.